Hello, welcome back to the channel. So again in this video I'll be continuing with molecular point groups, and with this video we'll be completing our survey on different kinds of molecular point groups. So now in this video we shall see about octahedral point groups. So in octahedral we can have O and OH, two different point groups, and then even we can have a look at icosahedral point groups which are I and IH. Okay, first let's so where we are. So point groups, it can be classified into molecules with low symmetry, molecules with high symmetry, and molecules with special symmetry. Under this heading, mainly what I can say is that linear point groups, they are of one kind, and remaining all they are of other kind. So in this also we can have tetrahedral point group, octahedral point group, and icosahedral point group. So in my previous video I have completed this tetrahedral point group. All these three they were covered. Now in this video we shall look at these 4 point groups. Octahedral, under octahedral point groups we will have 2 O and OH, and similarly under icosahedral we will have I and IH. So these 4 we shall have a look at. So among these 4, octahedral OH point group, that is very important to us. Definitely we should understand all the symmetry elements and symmetry operations present in this group. So if we can understand octahedral, fine. Even this O, it can be understood. If we can understand OH, O can also be understood. I and IH, they are not of that importance because very less number of examples are available. Of course, for all these special cases, we have very less number of examples, and they are not that common too, especially when it comes to this O, I and IH. So we shall see this OH point group in detail, and remaining point groups just we shall have a glance. We shall take a glance over these point groups. Okay, let's begin. So first I'll take the important one, OH point group. So this comes under octahedral, and order of this, it will be 48, which means that 48 different symmetry operations will be possible over this octahedral point group. So we shall see the details which all operations are possible and how we can easily understand them. With a cube example we shall understand that, and before that some common examples. Any perfect octahedral molecule like SF6, very important thing here is that all bond lengths, all 6 bond lengths, they should be equal, then only the point group it can be called as OH. So if some cases, sometimes in coordination compounds, if we have unequal bond lengths because of Ion-Taylor distortion and all, then definitely the molecule, it will not be OH, and it will deviate. It will usually go to D4H. Okay, fine. But this example, this coordination complex example, this is a perfect octahedral complex. So this is an example, and this octahedral complex as well as cube both have got same number of symmetry elements and same number of symmetry operations. Therefore even simply cube, a solid geometry cube, if it is considered, that will also go to this point group itself, right? Even octahedron, a solid geometry octahedron, that also goes to this point group itself. And further, any perfect octahedral molecule. And cubane, so cubane molecule, it means it will have atoms, carbon atoms at just corners of a cube. That molecule cubane, that also goes to this point group itself. Fine. Now let's try to understand all these operations with the help of this diagram. So this is a diagram of a cube. Let's say here we have atoms. Even if we do not imagine atoms, in that case also this solid geometry cube, that will belong to this OH point group itself, and for convenience definitely we can consider atoms here. Otherwise, if we consider that this is a octahedral molecule, definitely an octahedral molecule can be placed inside this, so that the central atom, it will lie here at this position, and other 6 atoms, one it will be at this face center position, the other one it will be at this face center position, the other one it will be here at this face center position. So totally 6 different faces we have for this cube. So we can imagine a octahedral molecule inside cube in such a way that the central atom, it lie at the center of the cube or body center position of the cube, and the remaining 6 atoms, they will be at the face center position, so that even a octahedral molecule, it can be conveniently placed inside this cube, and symmetry operations on that molecule also can be demonstrated with the help of this cube itself. Now let's try to understand this as cube itself. See, first thing, this axis, it can access C4 axis. We can easily understand that on this axis 90-degree rotation is possible, so that this atom, it takes this position. Similarly all atoms, they change the position, so this axis, it is C4 axis. And it's not just one such C4 axis. What we have is 3 C4 axis we have. So in this case, essentially we have 3 C4 axis. So one, it is this, the other one it will be like this, and the third one definitely you can imagine it will be just like this. So mutually perpendicular 3 C4 axis will be present. Then along with that, C3 axis are also present here. So C3 axis, how they are present? So we should just take any two corners. Let's say this corner and this corner have taken opposite corners, and I should join them. So on that, the cube, it can be rotated so that these three atoms, if you can see, these three atoms, they change their positions. Therefore, this axis, it is C3 axis. And how many such C3 axes are present? That can be very easily understood. So to construct one C3, what we need is two corners, and for a cube, 8 corners are present. So therefore, 4 C3 axes they are present. In fact, to consider a molecule to this octahedral point group, this is the necessary requirement. It should have 4 C3s and 3 C4s. If you can compare, or if you remember tetrahedral point groups, in case of tetrahedral point groups, 4 C3s they were there. Along with that, 3 C2s used to come. But here 4 C3s plus 3 C4, that takes any molecule to octahedral point group. Further, it can be O or OH. Fine. Now, to demonstrate or to see other symmetry elements, we can have 6 C2 axes in case of a OH molecule, right? Of course, these symmetry elements whichever are present here, all these 3, these are there even in the case of this E2, this C2. All these they are there in the case of simple O point group 2. So in addition to that, here whatever elements I have listed, they are there only in OH. We shall see when we go to O point group, right? So this 6 C2s, that can also be easily understood. So to get a C2, what we are supposed to do is we should take any two opposite edges. Say, let's say this is a edge and this is a edge, and now I take the midpoint of those two edges and I pass a axis through that. So now you should be able to imagine. So if I rotate the molecule on this axis, that will 180-degree rotation on this axis, that will result in identical orientation. We shall see all these operations in 3D animation, but it's better we should try to understand that in 2D diagram itself. So maybe this atom, it takes by 180-degree rotation, it goes to this position. Similarly, this atom, it takes the position by 180-degree rotation, it will result in identical orientation. It will be difficult to imagine which atom goes where here. And now, how many such C2 axes are present? So to construct one such C2, what we need is 2 edges. And for a given cube, we have 12 edges. Therefore, we can say that 6 such C2s are possible. Then along with that, we have inversion center that can be easily understood, that is present at exactly center of the cube. Inversion center is present. And we have some planes. See, we have some sigma h. So sigma h, it can be easily understood. So this is one sigma h, because what we consider is we can have a axis like this, that can also be considered to be principal axis, that will be C4 axis, and this is perpendicular plane, therefore this will be sigma h, and not just one sigma h. So we have 3 C4 axis, perpendicular to that 3 sigma h are possible, 3 perpendicular planes are possible. One such sigma h has been demonstrated. The other one, it will be something like this, it will be here like this, and the third one, it should be like this, it should go like this, that is sigma h. So not only that, along with that, 6 sigma d's are present. So sigma d, 6 sigma d's, they are the even feature of tetrahedral point group, but here also we have sigma d's. So how those sigma d's can be understood? Very easy thing. So we should take 2 edges and completely we should join 2 edges, and the plane that joins these 2 edges, that will serve as a sigma d, because this passes in between subsidiary axis. So in this case, subsidiary axis, it will be C2 axis. So therefore, we will have even sigma d's, right? And 6 such sigma d's are possible. Further, this C4 axis, it is collinear with S4 axis. Even S4 axis is possible in this case. So C4 axis, it is collinear with the S4 axis, and C3 axis, C4 axis, it is S4 axis too. C3 axis, it will be S6 axis. On this axis, the molecule, it can be rotated by, so if it is S6 axis, it should be 360 divided by 6. So that means it should be 60-degree rotation. So that 60-degree rotation followed by reflection in perpendicular plane, that operation is also possible. So S6 axis is also present, and in total all these symmetry elements and all these symmetry operations are possible. Let me just list it out. So E under E, one symmetry element, one symmetry operation. C3 axis, on C3 axis we consider two operations, because on a Cn axis n minus 1 operations are possible. So 4 such C3, so 4 into 2, 8 operations are possible. C4 axis, similarly on C4 axis, each C4 axis, on that we can perform 3 operations, n minus 1 operations. So 3 into 3, 9 operations are possible here. And on C2 axis just one operation, so 6 such C2, 6 operations. And even on planes just one operation, 3 sigma H, 3 operations, 6 sigma D is 6 operations, one inversion center, that is one more operation. And on S6 axis, on each S6 axis you can just work it out. Proper improper operations, what I should say, pure improper operations, improper rotations, they will be in fact on each S6 axis. 2 such improper rotations are possible, or S operations are possible. So therefore it will be totally 8. And similarly on S4, 3 such S4s are present. On each S4, S41 and S43, those are truly improper operations. So totally 3 into 2, 6 operations. And if we just take a sum of all this, all 48 operations, totally 48 different symmetry operations are possible on all these different symmetry elements in the case of octahedral molecule. Now let's try to see this on a SF6 molecule. SF6 essentially it's octahedral molecule. Let's try to understand all this on a SF6 molecule. So this is SF6 molecule, which is a octahedral molecule, and which goes to OH point group. So now let me demonstrate all different possible operations in this case. So first we shall consider say C3 rotations. So we know in case of octahedral molecule, we can just join 3 atoms to make a triangular face, and at the center of that triangular face, C3 axis it exists. So now this is C3 axis. So on this axis I can rotate the molecule by exactly 120 degree to get identical orientation. Therefore this is C3 axis. Now along with this, the molecule it has, and C3 axis we know, so in total it has 4 such C3 axis. This is one. So if at all I have to show all C3 axis, see all these are C3 axis in case of this molecule. 4 different C3 axis they exist. How 4 C3 axis are present, that has been described in today's diagram. Now let's go to C4 operations, and we know that 3 different C4 axes are present in case of this molecule. So first let's consider C4 axis. So any 2 opposite ligands, if you call these as ligands, that if you join that axis, it will serve as C4 axis. The molecule it can be rotated on this angle by 90 degree to get equivalent orientation. Therefore this is C4 axis, and see this is one C4 axis. Along with that 2 more C4 axis they can be shown here. So as we can see this is one more C4 axis, this is one more C4 axis, totally 3 C4 axis they exist. So along with that, even we have some C2 axis for this, 3 C2 axis they do exist for this. So where those C2 axis? So this is collinear with this is C2 axis. See, now this axis is definitely different from the axis which we have considered earlier. In fact, even we can consider that this axis it can serve as C2 axis, but operations on this C2 axis I had considered it along with C4 axis itself. So this C4 axis it was not considered separately. Now different C2s are possible. So these different C2s, so this is to bisect any octahedral bond. So this bond angle it will be 90 degree. So if we can put an axis at 45 degree, so that will serve as C2 axis. So how it acts as C2 axis? See, we can just rotate the molecule on this axis by 180 degree to get identical orientation. And now 6 such different C2 axes are possible. 6 different C2s are possible. So all 6 C2s we can see here. Fine. Then coming to improper, so improper operation, in fact in this case it's not that difficult to understand. So this S4 axis, C4 axis, this even it serves as S4 axis. So let me just show that. So this S4 axis, easily it can be understood that it is even C4 axis, it is even S4 axis. And very interesting thing, so let me not demonstrate operations on this S4 axis. So more important is S6 axis in this case. Earlier which I had mentioned as C3 axis, on the same axis we have S6 axis collinear. Now it is not just say direct proper 120-degree rotation which leaves us the molecule with equivalent orientation. Now it is S6. So S6 means 360 divided by 6, that means 60-degree rotation followed by reflection. So one such operation I can perform. See, the molecule, it is rotating by an angle of 60 degree, and then it goes reflected back, and that leaves the molecule in original orientation. Therefore S6 axis it is possible, and so it's this S6 axis, it's collinear with C3 axis, right? So sigma h reflections, it can be understood, it's not that difficult in this case. So sigma h reflections, so 3 reflections or 3 sigma h are possible. So just we can consider all 3 simultaneously. These are sigma h. Along with this 6 different sigma d operations, they were also possible. Maybe one at a time I can show. See, now this is, in fact, it is considered to be sigma d operation, because this is sigma d, it passes in between 2 perpendicular C2 axis. That's how this is sigma d. So you can just play with this kind of molecules, and same set of symmetry operations, they are possible in case of molecule cubane, or if you consider CrCO6 octahedral, perfect octahedral complex. In all these cases, same number of operations they are possible. So these are total different operations possible on OH point group. Okay, the next one, it is O. Again, it's pure rotational point group, as it was mentioned earlier. So this is the necessary requirement, 4 C3s and 3 C4s, that is necessary requirement to take any molecule to octahedral point group. So when these are present, automatically even these 6 C2s, they will be present. So only rotation operations are possible, and as described earlier, just if you consider different operations which are possible on all these proper axis, it will sum up to 24. So 24 different symmetry operations are possible in O point group. So examples for this, rare examples, one is this dodecaethylene octamine. For this, you can just follow symmetry at Otterbein, so that you can find this structure. Little difficult to understand, rather this can be understood very easily. V6 P8O24 core, so that's also example for this O point group. So this has been given, this you can find it here. So I'm not demonstrating the animations for this. So just whichever symmetry elements are possible, quickly I'll show that. So in this case, what you can find is C4 axis, and 3 such C4 axes are present. So this is first one, and this is second one. Third one, it passes exactly like this. So that is C4 axis. And in this case, some triangular type things you find, say here, if you can notice. So on this, if you can consider an axis which passes exactly at the center of this atom, so that axis it will serve as C3 axis, and 4 such C3 axis will be possible in this case, and even 6 C2s are possible. So this is not that important example, or not that important point group. Those who are interested, just can go through symmetry at Otterbein site, and you can try performing all symmetry operations which are possible on this molecule. Fine. The next one, it is icosahedral point group. Icosahedral, here also we have two different point groups, icosahedral I and icosahedral IH. So first let's see I. So this I, again, it is pure rotational point group, just like T and O, pure rotational point group. So different operations that are possible here. The characteristic feature is this: we will be having C5 6 different C5 axis, and along with that 10 C3s. So this will be the essential feature of a molecule which goes to icosahedral point group, and along with that 15 different C2s, they will also automatically come, and all the different symmetry operations that if you take the sum, you can just verify whether these are correct or not. On 10 C3, definitely 20 operations should be possible. On 15 C2, 15 operations. On 6 C5, on C5, 4 operations. So 6 C4, 24. So total it makes 60. So one example for this is stub octahedron. So again, just some axes they have been identified. So we have so many triangles here, and so many pentagons. So at the center of the pentagon, we can expect a C5 axis. The molecule, it can be rotated on a C5 axis to get identical equivalent orientation. And how many such C5? 6 different C5s are present. And C3 axis, we have triangles, and not at the center of all triangles. So the triangle which is surrounded by 3 more triangles. So center of that triangle, from that center we can have a C3. In opposite direction also similarly it should pass through the center of a triangle which is surrounded by 3 more triangles. All these things you please verify. So 10 such C3s they can be identified in this case, and C2s, 15 C2s are possible. So one such C2 it has been indicated here. So purely rotational point group. So this is now octahedron. Again, this also not that important one. So I'm not demonstrating 3D animations for this. And even if I demonstrate 3D animations, to understand this, you should perform all these operations. Then only you can get the feel of that. So please do visit that site and try all these operations. Okay, the next point group that we are considering is icosahedral Ih point group. So we have seen icosahedral I point group where 6 C5 axis and along with that 10 C3 axis will be present, and in addition to that even 15 C2s they were there in the case of I point group. Now, so this icosahedral IH point group, even that has all this. So therefore those 60 operations which were possible in I point group, those are possible here also. Along with that, in addition to that, we can have inversion center here, and each C5 axis it will even serve as S10 axis, and on each S10 axis genuine 4 improper operations are possible. Improper axis operations are possible. Say if you consider S10, it will be S10-1, S10-3, then S10-7 and S10-9. Whereas S10-5 it will turn out to be inversion center I. So therefore that has been left, and what we can have is just 4 operations on each S10 axis. That's how 6 into 4, 24 different operations are possible. And this C3 axis, which was proper axis, that will even serve as S6 axis. So on S6 axis again, on each S6 axis, what we can have is 2 genuine improper operations we can have. So it should be S6-1 and then it should be S6-5. S6-3 again it turns out to be I in this case. So therefore on each S6 axis genuine improper operations there will be 2. So 10 into 2, 20 operations are possible, and 15 different sigma are possible in this case. So and this makes a total of 60, and in total 60 plus 60, 120 different operations they will be possible in case of this point group, IH point group, right? So very less number of examples are available. One such example, it is this buckyball. We know this C60. So Buckminster Fullerene. So that it goes to this icosahedral point group. So just one C5 axis. So this you know that this is made up of 6 membered rings and 5 membered rings. So this is made up of 12 5 membered rings, and it should be 26 membered rings. If I'm not wrong, this Buckminster Fullerene, it should be made up of 26 membered rings and 12 5 membered rings. So each such 5 membered ring if you consider, so 2 such 5 membered rings, they constitute one axis, or center of these 2 rings if you consider, if you pass a axis, that will serve as a C5 axis, and therefore we can have 6 C5 axis in case of this icosahedral point group. Similarly, if we pass a axis between 2 6 membered rings, I am talking just in case of this molecule. So 2 6 membered rings together they'll constitute one C3, and therefore total 26 membered rings, that will give us 10 C3. And this C3 axis it will even serve as S6 axis, and this C5 axis even it will serve as S10 axis. So along with that 15 sigmas are also present. So one such sigma it has been indicated, but in reality 15 such sigmas are possible, and therefore 120 different operations will be possible on this molecule, and this buckyball it goes to the point group IH. So we can have even other examples like dodecahedron. So this is dodecahedron. It is just carbon atoms which are placed at the corners of dodecahedron. So this is the geometry dodecahedron. So this dodecahedron, it is just made up of 12 5 membered rings and nothing else. So as you can see here, one 5 membered ring we can see here. So 5 more they are surrounding like this. So this is just half of the molecule. The other half of the molecule, similarly, it will have 5 membered rings in this way, plus one exactly at the back of this 5 membered ring. So totally it will be having 12 such 5-membered rings, and this also it goes to this point group, icosahedral point group itself. So here C5 axis, as it was mentioned, it will just pass in between or at the center of each 5-membered ring. And now in this case C3 axis, it will be, say, if a axis, if it can be passed like this, we can see here, just from exactly one corner to its opposite corner, that makes a C3. And this C3 axis, it will even serve as S6 axis. This C5 axis, it will even serve as S10 axis. So I suggest all viewers to go through Symmetry at Dr. BM site and there check all these operations and convince yourself that all these operations, they do exist for this IH point group. Right, and one more sigma, 15 such sigmas are present, one sigma it has been indicated in this case. And totally, even in this case, though it is just made up of 5-membered rings, we can have all these 120 operations possible in case of icosahedral point group. So therefore this also it goes to IH point group itself. So with this we are concluding all different point groups, survey of all different point groups. Hope all these videos, they have helped you understanding all these different point groups in a better way. And definitely we should work with more number of examples and we should solve all different examples to get mastery over these concepts. Thank you for watching this video. Thank you again.